Hello guys, sorry if you had to wait for me. Turn on your cameras if you can. Well, all right. So what did we do last time? We ended up talking about geometric random variables. Yes, and just a brief recount. Geometric random variables are trying to figure out how many failures do we have to carry out until a first success appears. So the probability, if the trials are independent and each is successful with probability p, then the probability that we will see k failures before first success is 1 minus p to the power of k times p. So that's what is this number? We examined the cumulative distribution and we calculated the expected value. And likewise, as I mentioned, you can calculate the variance. You have to just figure out the expected value of x and then the expected value of x squared. Yes? And what you will end up having is 1 minus p over p squared. So then let's try to examine yet another distribution. It's called negative binomial distribution. And here what you do is, instead of just waiting for one success, you wait for a number of successes. Let's say we wait for r successes, right? So not only one success, but maybe 5 successes, and then you stop. So it's directly related to the geometric. It's just a generalization of it. Do you agree? The negative binomial is the geometric when r is equal to 1. You can see what happens. So what's the probability that you have to wait? Well, that you have to play how many trials? You have to play n trials. That means what? That means that altogether the game stopped after the nth round. And then of those nth rounds, the last round was a success. And before that round, we had additional r minus 1 successes. So what happened then? So out of n plus, so n plus r minus 1 is basically, so maybe I said it here, just to correct myself, here is the idea, right? So this is how many failures you gathered, of course, right? N is the number of failures that you gathered. And you had to accumulate r successes. So how many failures have you gathered up until the moment where r successes occurred? So altogether, what do we have? We have then, if x is equal to n, we had n failures, we must have had r successes. So n plus r minus 1, choose r minus 1, the very last trial was a success, right? So n plus r, the very last, the n plus r trial was the last success. So n plus r minus 1, among those trials, there must have been additional r minus 1 successes. Yes? And then for each of this, the probability is clearly p to the r, because we have exactly r successes, and 1 minus p to the power of n, because we had n failures. So this formula is clear, yes? I'm sorry if I'm a bit strange. I just why I came up. I was compiling. I was thinking about something rather different, and I'm not still recovered from it. It's a sort of thing like from a horror movie. Yes, it's. I can show you what this thing is. You see, just so that you understand what I have to go through. Not this one, but. This is basically me today. Yes. So forgive me if that will be So I'm trying to speak through to you, even though my consciousness is completely sucked out of me. Not quite. I mean, it's a horrible fractal. I tend to imagine I see meanings in those things, right? Very bad omens. Like people read things in their tea, and I read them in my fractals. What was that? That was something that when you see it, you will be glad if you could do probability even without sleeping, because this is worse. So back to this particular topic. Okay, guys, so again, we have x equal to n. We have n failures, right? And we have this formula. Please confirm if you understood. What is this, guys? You understand it? Please write y if you do. Okay, or do I need to re-explain it? Good, right? So you understand how this would have been obtained by a Kafka protocol or whatnot, right? So the last, why is it r-1? Because the n plus r trial was a success. And before that, we had r-1 successes, and they have to be distributed among this. So then we want to figure out how to calculate the expected value of this random variable. Yes. So what we can do is this trick, guys. So to compute the expected value, we don't want to do it directly. It would be hard, but we can observe that x is the number of failures before the very first success plus the number of failures between first and second success, and so on and so forth, until xr is the number of failures between r-1 success and the final r success. Yes? So what is the expected value of x? It's the sum of the expected values, agreed? Now, each of them, you can imagine, once a success occurred, then it's between one success to the next, the distribution has to be geometric. You agree? Because I mean, if the experiment consists of independent trials, there is no memory of what happened before. It doesn't matter. If you throw a coin, previous throws do not affect any new outcome. So it's as if you start from the beginning in the geometric case, and you throw the coin until it first is heads, right? Something like that. So what is that situation? What is the expected value of x1? It is the geometric expected value. It's 1 minus p over p. And the same goes for all the remaining random variables. And so this is what you get. Good? Now, what about the variance? Clearly, x1, x2, x3, and onwards, they are independent. You agree? In other words, the number of failures after the first success will not be influenced by how many failures we had before the first success. And so the sum of the variances is going to be giving us the variance of this, what do you call it, negative binomial. So then what we have is that the variance of x is r times 1 minus p over p squared. Good. And then you have this classic example of, I think it's called coupon collecting problem. So there are n types of toys in cereal boxes. So whenever you buy one of the boxes, you can find one of those toys inside of them. And they are equally likely to be any of the n toys. There is a total of n different varieties, and each box is equally likely to contain any one of them. Good. So we want to know, on average, how many boxes do we need to buy to get all the toy types? Yes, to complete the full sequence. So how can we solve this problem? Well, we can say X is the random variable of interest. It's the number of cereal boxes that we have to gather until all toy types are collected. And then what is X? X can be written as X1 plus X2 all the way to Xn, where each Xk, so X1 is the number of boxes you buy until you get the first new toy, right? X2 is the number of boxes you buy thereafter until you get the next new toy, and so on and so forth. Good? Oh, good, right? And you can imagine just before I do it, guys, before I go through it, X1, what type of distribution will it have, do you think? Well, I mean, X1 is easy. X1 is the answer is obviously 1, right? X1 is as soon as you buy a box, you get a toy. What about X2? What distribution will X2 have? I don't ask, I don't mean for you to calculate the exact parameters of that distribution, just what distribution, what sort of random variable would it be? Think about it. So it will be failure whenever I get again the toy from first box. Do you agree? I have box 1 prime me. Now I know which toy is old, and now when I get the same toy in the box again, I mean, you're giving me some formulas, but I mean something much simpler. Distribution just means what sort of probability function do you have assigned to the trial? So how many new boxes do you have to buy until you get the next new toy, right? So we got toy number 1. You agree? If I buy the next box, I can get toy number 1 again. And then I have to buy another box, and maybe I still get toy number 1. Yes? So we have probability of failure is pretty much 1 over n, because we know we have one of the toys is already obtained, right? And 1 over n is that we obtain the same toy again. That's failure. We haven't obtained a new one, right? So x1 is just right away it's equal to 1, but x2 is having a geometric distribution. Yes, so not so much the number that I asked you to figure, but name the distribution. What type of distribution? It has a geometric distribution. Do you see that, guys? No? You don't look like you see it. Here is what happens. So imagine you have a toy 1, 2, 3. So you buy the first box and you got toy 1. Yes? Now, what is x2? X2 is equal to number of additional boxes until new toy. Yes? How many additional boxes do we need until new toy? So what can x2 be equal to? X2 can be equal a number of additional boxes until the box of new toy. So it could be equal to 0, and that implies that second box. So this was box 1. So that means this immediately the box I get is either 2 or 3. Yes? Or if x2 is equal to 1, that implies I get the next box, right, that I buy is 1, failure. And then the next one is maybe 2, maybe 3. You agree? You see what I'm saying, right? So it's exactly a geometric distribution. Why? Because what is the probability that x2 is equal to n? What's that probability? That probability is equal to, if I have toy 1, 2, and 3, whatever was the first toy, the probability that we have to do it n times is what? Is the probability that we fail n times. It means in this case 1/3. We failed n times, and then successful we can be here with probability 2/3. Right? That means we had n times that we received, again, toy number 1, let's say, right? And then the next time after n trials, I finally got either toy 2 or toy 3. And that's what happens here. So it's a geometric distribution. And so you can see in general, I can calculate. In general, it's not so difficult to calculate the probability that xk is equal to j. So what is xk? Xk is the time between the number of boxes I gathered between the k-1th new toy and the kth new toy. Are you following? Well, I mean, Gustavo, I think, first of all, you can you can still get all the toys you have, right? So it's you can if you whatever n toys, you will always get one of them, right? But what's updated is what's considered a new toy and what's considered old toy. So the probability of success increases each time you gather. Sorry, decreases. The probability of success decreases, right? Each time you gather new toys, there are many of them are older, and now it's you can see like to gather the very last new toy, that's the hardest. That should take the longest. You agree? Because if you have, let's say, 20 toy types and you already gathered 19, there's lots of ways that you would fail. You would buy a box, and it's very likely to be one of the 19 and not the 20th, right? Yeah. So so here, what do we have? So what's the probability that xk equals to j? Xk equals to j means what? Means I have k-1 old toys. Do you agree? K-1 toys are old, so the probability I pick the old toy is k-1 over n each trial. And this means what? This means I have undergone I mean, I think in my notes I made it differently. I mean, so j means that I include also the last box, you see. So it's not exactly geometric, it's very close to it, though. But you see, so here I'm assuming that I count all the boxes together with not just the boxes until the success, but I decided to count both failures and success. It's very similar, right? So j boxes in total, and the last one of them is the toy. So that means k-1 over n to the power of j-1. And this is the probability of the success on the last trial. Yes? And then I just decided then because of that, because it's not exactly a geometric, I made it slightly different. It's basically geometric plus, it's very close to geometric. It's geometric plus 1. Do you agree? It's the same, the expected value of it could be just calculated as the expected value of geometric plus 1. But I just calculated it from scratch here. Right? And blah, blah, blah. I calculate again from scratch. And what I get is, again, you can see this is the expected value of the geometric plus 1. You didn't have to do that. You could just say, well, it's geometric plus 1. So you could just right away see this is the expected value of geometric, and plus 1 is 1 over p. But I did the calculation from scratch. Yes. So the answer is 1 over p, where p is the probability of success. It's changing with each trial, right? And so what is the expected value of x? The expected value of x is the summation of those numbers, which are 1 over p, right? For there is for 1 there is a 1 over p, for 2 there was 1 over p, and then when you factor it out, you see it's the summation of 1 over n plus 1 over n minus 1 all the way to plus 1. So it's n multiplied by the nth partial sum of the harmonic series in this case. You see, this is the expected value. And you can see it will go to infinity, yes? And that makes sense. The more toy types I have, the longer it will take me to gather the boxes. The more I will have to buy on average boxes until I get my full collection. So for instance, if there are 5 toy types, then this average that you will have to buy is about, well, I would say 11.4 boxes on average, which means expect to buy 12 boxes or so, right? Between the average is this number, so you buy somewhere between 10 and 11. But I mean, you need to calculate variance to know how likely it is to be much more, how likely it is to be less. That's just the expected value. Yes. And then you have another thing, which is, I always forget the names. So this is called negative binomial. And then we have yet another distribution called negative hypergeometric. Yeah, I never remember it. Don't bother. Just, you know, when you see the problem, you should figure out how to deal with it. Urn contains W white balls and B black balls. The balls are randomly drawn 1 by 1 without replacement until R white balls have been obtained. I see what it is. Yes, so it's very similar to the previous distribution, but there the success of each trial was independent of the previous trial. Here, that's not the case. Yes, so here you are going to sample 1 by 1 until you obtain the R white ball. So we have W white, B black, and you are going to sample until the R white ball is obtained. Make sense? And X is the number of black balls in the samples, the number of failures. It's a very similar distribution, except it's without, you know, each trial is not independent. Yes. So then we want to understand how to calculate. We can compute the probability that X equal to K directly, and here is what we can do. So here is my Kafka protocol. So if X is equal to K, we want to construct a success protocol. What does it mean for X to be equal to K? It means I've gathered how many? I've gathered K black balls. Yes. And altogether, I had to gather R black balls to be done with, right? So sampling sequentially without replacement might be viewed as sampling things either, I mean, I show it here sequentially, but you can do that, imagine pushing them out in one scoop. That's the last expression here, yes? So what do we have here? You have here, okay, we have gathered which exactly are white balls that we have gathered. We list them here in order. Which K black balls have we gathered? We list them here in order. And which was the last white ball? I decided to do it this way, right? So among those ones, which of them is it first position, second position? Which of them was the last to stop this process? And order of remaining balls is what? So order of the remaining balls is simply take R plus K minus 1 and factorial, because they can be arranged in any order, right? The last is the white ball that stops it, and all the previous black and white balls can be rearranged. So this is what we get. Yes, that's numerator. Now the denominator is simply what's out of how many sequences, right? So the denominator is W plus B, choose R plus K. So because here I mean, this is a sample of size R plus K, and each R plus K balls are equally likely to be sampled. So it would be W plus B, choose R plus K times R plus K factorial. And when you simplify, this is the formula that you can obtain. And we can obtain a simpler formula if we want. This is the simpler formula. And this is how it will work. This is a bit more interesting. So what happened here, guys? So we have we can imagine that we have a total of W plus B balls, and when we sample those balls, what we have is that some of them become white and others, we don't sample randomly, we just sample a bunch, and some of them become white and the others become black. Yes. So we have in my sample, I must have R plus K balls, right? So R plus K, the last, so in the sample you have R plus K, one of them is white, and among the remaining ones, exactly R minus 1 have, so to speak, decided to be white. And from the balls that were not sampled, that's W plus B minus R minus K, exactly W minus R decided to be white. Make sense? So it's like this idea of that we sample first and then they change colors. Right, so any and in general any W plus B can decide to be white. So those are the ones that decided to those are the ones that decided they are labeled, you might say, 1 through W plus B, ball numbered R plus K decided to be white, and then of R plus K minus 1, which previous balls decided to become white. Yes? Make sense? This is difficult. Yes, and this reminds me, of course, I'm not sure, just when I, so it reminds me of what did I think of it, right? So it reminds me of a jellyfish, right? So, когда пленясь прозрачностью медузы, ее коснемся мы капризом рук, она как пленник, заключенный в узы, вдруг побледнеет и погибнет вдруг, which roughly means when you're captivated by the transparency of the jellyfish, you decide to touch or hold this jellyfish in your hands. Like a prisoner, she turns pale and dies suddenly, right? So it's kind of like this. So you touch those balls and then they change color. Or if you like more, okay, let's see. So how do we calculate the expected value? That's the hardest thing here, of course, how to calculate the expected value for this one. So we can again do the same thing we did for the negative binomial. We can set x equal to x1 plus x2 all the way to plus xr, where each xk is the number of black balls between k minus 1 and kth white ball in the sample. Yes? So what you can imagine in trying to calculate the expected value, imagine that what you have is this situation, right? So you have the white balls are numbered 1, 2, 3, all the way to W. And between them, you have gaps, right? Between them, you have gaps. And then the question is, so because we stop after once we reach the rth white ball, we have our full sample. We stop this, right? So the sample is all the way to the rth white ball. So then before this one, which black balls are here? Which black balls are here? Which of them are here? Which of them are all the way to XR is the space between R-1th and rth white ball. Good. And so then we want to actually, so xk is the is then of course between the k-1th and kth white ball, right? How many black balls can there be there? So there are black ball 1, 2, 3. They're all the way to B. Those are the labels of the black balls as well, right? So there are B black balls. So we can break this. This expected value is still hard to calculate, even of xk. So we break it even further, right? So we have summation of summations. So how do we break it? We will define xk to be yk1 plus all the way to ykb. And this random variable yk1 will figure out whether or not black ball 1 is between k-1th white and kth white. You follow, right? And it will add 1 if it's there. That's what they will do, right? So what's the expected value of ykj in general, right? So for a fixed k, what's the expected value of ykj? Well, that's the same as the probability when it is equal to 1. Right now, where can the first, or where can the jth black ball be? It's equally likely to be here, 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 or all the way to W plus 1. You see, it's equally likely to be on any of those trays. So the probability is 1 over W plus 1. Do you see that? The probability is in any of the places is 1 over W plus 1. So the probability is in the kth place is 1 over W plus 1. Yes, and so the expected value, and it's true for any j. So the expected value of x sub k is b multiplied by the expected value of 1. It's true for any of them, right? The same assessment. So this is b over w plus 1 is the expected value of xk. Yes, and then what is the expected value of x? It is simply, we have how many of them? We have x1, x2, we have all the way to x sub r. So we have r times expected value of x1. Each of the x's are the same. You see, you can see by symmetry that the distribution should be the same. The number in here and the number in here and the number in here are, expected value should be the same. So this is pretty difficult. So the expected value of x is this number. It's r times b over w plus 1. Were you able to follow more or less, guys? Yes? I hope so. And now, what about calculating the variance? Now the variance we know that it's not the sum of the variances. Do you agree? It cannot be, because the outcome for x1 affects the outcome for x2, right? Because we have fewer balls to sample. So, but the variance is equal to the sum of the variances plus all the combinations of covariances, and you can see by symmetry that the combination of any two of them is the same as the combination of any other two. Yes? x1 depends as much on x2 as any other combination, as any xk and xj. So that means that what we have is the variance is r multiplied by the variance of x1 plus r times r minus 1 by covariance of x1 and x2. That's the variance. Now, what do we need to do? Well, we know that first we know that, for instance, x1 is equal to y11 all the way to y1b. So we know that for instance, variance of x1 is equal to b times, those are the ones that we can say are independent, you see, because the position of this means where is, we are asking, is the first black ball, is it in position 1? And then we are asking, is the second black ball, is it in position 1? So they are independent. They don't have to be, where the first black ball is located does not affect the position of the second black ball. So we know that variance of x1 is b times variance of y11, and the variance of y11 is the expected value of the squared minus the square of the expected value. This is 1 over w plus b as before, minus this 1 over w plus b squared and multiplied by b. And this is the variance of x1. Now to calculate covariance of x1 and x2, that's the expected value of x1, x2 minus expected value x1, expected value x2. And that's the same as minus expected value x1 squared. Now, what about the expected value of x1, x2? That's the expected value of the product. Yes? This is x1 and this is x2. And now what happens here? Now, the way it can be equal to 1 is when they are, we have the situation when they are okay, the first one, yes. So when I multiply it out, what do I get? I get several types of combinations. I have combinations where the first index is where the first index and the second index are kind of are matched, like this, like 1, 1 and 2, 2, or so yes, how I calculated the variance. Are you with me still, guys? The variance was okay. I just don't want to lose you. It's very difficult calculations. So with covariance, I need to know what's the expected value of x1, x2. And then that's the expected value of the product of those two parentheses. Yes, so when I cross multiply, I can then expand it. You agree? Cross multiply and expand it. And then what do you see? You see here that you have different. You have a combination of indices. You have indices where the second number is identical, right? So here we have 1. And here we have 1, right? So where we forget about the first index, look at the second number. So we have, for instance, y2b and y1b. Yes, so there is second index is a b. It's identical. Yes. And we have those that are not identical, as in there is a 1 and there is a 2 here, right? When you multiply it, you have identical and non-identical. So how many identical do you have? Clearly 1, 2, clearly B identical, right? And the expected value for all of them is the same. So it's B times the expected value of any representative. And the non-identical ones, how many can you have? Well, you can have one from here, one from here, right? So and we'll consider only the second index, right? Second index. So so I decided to list it as B times B minus 1 because it's B choose 2 multiplied by 2 if I don't care in which order to write the index, right? So I want to write it, let's say maybe its combination here might be second index is 2 and second index is 1, or second index is 1 and second index is 2, like I wrote over here, right? So forgetting about the first index, ignore it for a moment, right? You just have the second index is here 1, and for the other one it's 2. It could be 2 on the left, 1 on the right, and vice versa. Yes. So so then altogether you have B times B minus 1 of them, and here I place them, you know, second indexes in order, and this is a typical representative of this product. Right now, what is this now saying? So the first part here is saying that ball number second is black ball number 1 is in the first slot, and also ball number 1 is in the second slot. Clearly, that's never happening. Clearly, the probability of that of both of them, of y11 and y21 equaling to 1 is 0. So this is 0. Right, so this is gone. This is not important. What about this one? Can that happen? Yes, it can, right? Because this means ball number 1 is in the first slot, and ball number 2 is in the second slot. By slots, I mean here. This is first slot. This is second slot. Yes. So this we can easily know when it happens. That means that this is equal to 1 and this is equal to 1. Yes. Now, what's the probability this equals to 1? This is equal to 1 when it's 1 out of W plus 1, because black ball number 1 can be in any of the W plus 1 slots, and this equals to 1 independently, right? It's ball number 2 is in any one of the slots. So it's also 1 over W plus 1. That's why the number here is 1 over W plus 1 squared. And so the expected value of x1 times x2 is simply b minus 1 times this probability. Here it is. Yes, and then covariance is what? It's this number that we calculate from the product of expected value minus the square of the expected value of let's say x1, which we already know from before. And when we simplify, this is what you get. Right, and then what is the variance? Variance is R. And okay, check my calculations. I said hopefully nothing is wrong here. So it's R times variance of x1 plus R times R minus 1 covariance. So when you finish the calculation, then this is what you get, right? If you have the variance, if you have the covariance, just combine it, and this is what apparently you should get. Did you lose consciousness?
You answered my question, Professor, already. I wanted to ask why covariant, it's R multiplied by R minus 1, but during somewhere you were calculating B
Right.
B choose 2, then I understood, yeah, R choose 2, yeah, R choose 2.
This is, guys, a hard calculation. I do not know, and I'm rather out of my mind today, but I hope you understand me. And try to calculate it on your own. You see, just you have this problem. You understand the idea. It's this. So you have a sample, right? You have W white balls, B black balls, and then you are going to remove balls until you have gathered R white balls. You understand? And you want to know how many black balls are there. Make sense? So it's very similar to the negative binomial, except there's no replacement. You gather that, right? So just think about this problem, guys. Think about how to set up probability. See if you can do it without looking at my notes. And then how to calculate expected value and the variance. It's very hard to calculate. I think even probability is easier to at least have a formula for it than to calculate expected value for this particular situation. Make sense? It's a difficult problem, and if you're and then you see what idea we had. The idea is of course just look at white balls. You can imagine, doesn't matter where they are. I imagine that I actually sample this way, right? So I have a PES dispenser, and I just and then in this PES dispenser there is just first white, second white. I mean, I don't really need to move them. That's kind of the way I think of it, right? And then which black balls are in which region. Yes. So think if you can do that on your own. All right. And now we are finally able to talk about the Poisson random variable. So a random variable that has the Poisson distribution looks like this, guys. The probability that x equals to k is e to the minus lambda, where lambda is a positive number, times lambda to the power of k divided by k factorial. And you can check that this does sum up to equal 1. Because what's this probability? It's e to the minus lambda times the geometric expansion for e to the lambda. This is it here. And it's equal to 1. Where do you go, guys? Cameras. This is equal to 1. Probability that we get that x will be equal to k is called the Poisson function. Now, let's try to understand why the Poisson might be useful. How do we come up to study such distributions? So this is the key reason why it's a useful distribution. Imagine that you perform a binomial trials. We perform many trials. Each trial has very little chance of success. Okay, so very many trials, and it's billions of trials maybe, but the probability of success is so minuscule that that it ends up that the number of successes, even among, let's say, billion trials, is very small. Okay, and let me show you why that will have roughly a Poisson distribution. You can approximate using this function. Okay. So imagine x is binomial random variable with parameter n and p, and the product of n times p, that's the expected value of the binomial, is very much smaller than n. Yes? That the average successes, you perform many trials, but the average successes are very little. Then the probability that x is equal to k is approximately a Poisson with parameter lambda, where lambda is the expected value. It's n times p. Okay, guys, are you with me? This is important. The previous distribution was just hard, but this one is important. Right? So what happens? So let's see what's going to go on. So probability that x equals to k, it's going to be n choose k, p to the k, 1 minus p to the n minus k. That's just binomial, yes? And when I expanded, this is n factorial, k factorial, n minus k factorial, and all the stuff, right? Now, I can relate it to the expected value. You see what I do with p? I multiply by n and divide by n. Do you see that? And I do the same for this p. And then what do I get? This is now lambda to the k, and this is 1 minus lambda to the n minus k. And this here, the n factorial and n minus k factorial, I simplify, and I have here n minus 1 all the way to n minus k plus 1 over what? Now you see that here I can borrow out. I can borrow it's lambda to the k, and I have n to the power of k, which is moved here. You see that? You see the manipulation, guys? It's divided by n to the k, all right? And this is lambda to the k, and what is this? This is simply 1 minus lambda over n, to the nth power divided by 1 minus lambda to the n to the kth power, and I took the k factorial, the 1 over k factorial, and I placed it here. Now, what happens here? You see, guys, I can distribute the n. It's this over n, this over n, this over n, times lambda to the k, times this expression, divided by this expression times 1 over k factorial. Now, n is very large. It's very, very large compared to k. Okay, because I'm not going to ask for probability of n choose k where k is large. I mean, we're assuming where I'm not going to get lots of successes. I'm going to get very few successes, maybe 5, maybe 3, and when I perform millions of trials. Yes, so k compared to n is very small. So this number and this number and this number is very similar to n divided by n. You see, so you can see in the limit as it goes to infinity, this is equal to 1. So those numbers are very similar to the number 1. Right? The average lambda is small compared to n. So what do you see here? This expression, you can see it over here. This expression is simply the limit of e to the minus lambda. This is very similar to e to the minus lambda. This, on the other hand, because we just take it to the power of k, it's just lambda divided by n. It's a very small number. It's like 1 to the power of k, which is 1. You see? So this, so what do we get? We get this is about 1. Let me just underline it for you. So this is approximately equal to 1. This approximately equals to 1, whereas this approximately equals to e to the minus lambda. Yes? And what do we get? Look at it. Here is this entire line. We just simply see that it's very similar to 1 times lambda to the k times e to the minus lambda divided by k factorial, which is exactly the Poisson distribution with parameter lambda. Okay, now let's look at an example. So a newly published book is carefully examined and found to contain on average 1/2 typographical errors per page, which means per 2 pages you have 1 typographical error. Make sense? You open to page 100. What is the probability that you will find 1 or more typographical errors on this page? Okay, so let's try to understand what's the situation. I mean, we can imagine Poisson is actually more versatile, but we can imagine that on a page, on a given page, there's a lot of things written, and we have each letter we can presume is independently likely to be incorrectly typed. The assumption is not necessary, but for a moment, let's say each letter is independently likely to be incorrectly typed. Right? So how many letters do you have on a page? Maybe hundreds, maybe thousands, right? And it's very unlikely, if it's carefully examined, that any of those letters will be incorrect, right? So let's say a P was replaced by a B accident, right? It's very unlikely. And what's found is on average, is the expected value. If you run this experiment, you find that that on average it's 1/2. The number of incorrect letters on a page is 1/2, which means what? If you had some large number of trials where n is the number of letters, right? N is the number of letters, where n is maybe 1,000, maybe 2,000. I'm not sure how many letters, but enough, right? And the probability of error is so small that that the average of this very large number n times p is 1/2. Okay, success means you found a mistake. Success is very unlikely. And even though you have many trials, still you find the average number of mistakes you find is 1/2 per page. So that means lambda n times p is 1/2. You see, I don't know the probability, and I don't even know how many. It's very useful here, right? You see, I don't know 2 things. I do not know the probability that somebody makes a mistake. I presume it's a binomial. I presume that it's like a binomial trial, but I do not know the probability that a mistake is made, and I do not know how many trials are made. But on average, because somebody averaged it for me, I found out that it's 1/2. So I know that n multiplied by p is 1/2. So if I set it equal to lambda, I now can approximate the probability that x is bigger than or equal to 1, which is 1 minus the probability x equal to 0, which is approximately, right? This is, by the way, not exact. It's the approximation. It's 1 minus e to the minus 1/2, which is about 39%. Okay, so the probability that that on page 100 we will find one or more errors is about 39%. Yes. Here is another example, even much better, that truly illustrates how this is working. So atomic clocks and a lot of things are based on alpha particle emission. Right, so there is a radioactive material, and spontaneously some atoms decay and they release alpha particles when they do so. So consider an experiment that consists of counting the number of alpha particles given off in a 1 second interval by 1 gram of some radioactive material. Okay, so you have some instrument that measures it, and it counts how many alpha particles were released. Right, and on average, I mean, you do it for over several seconds. On average, you calculated it to be 3.2. You just did it for, let's say, 1,000 seconds. I'm not sure, right? Maybe a few days, and then you averaged over how many seconds passed, and you see per second 3.2 alpha particles are released. Now, we want to have an approximation to the probability that when we are going to run the experiment, no more than 2 alpha particles will be released. No more than 2. Okay, so first of all, how to understand this problem. So 1 gram of matter contains enormously many atoms, right? So 1 through n. I do not know how many atoms, but a lot, billions of them. I don't know. I mean, you can just check it, whatnot, right? Billions of them, right? And the chance that each one of them releases an alpha particle is minuscule. Do you agree? Because if it were larger, I mean, we will see thousands or millions of successes, but we see like what, 3.2, right? Out of billions and billions of atoms with 3 in 1 second, about 3.2, which means that the probability of success, the probability that an atom releases this alpha particle is so much smaller than the number of, it's so much tinier, so much tinier than 1 over the number of atoms available. So what do we know? We don't know how many atoms, we don't know the probability, but we know that n times p is 3.2. Yes. And so by that, you see, then by that if we apply this binomial reasoning, we would derive the same formula. So we would have derived lambda was said to be n times p. If you understood the derivation, you see why then we set the Poisson approximation to be with lambda equal to 3.2. So the probability that x is less than or equal to 2. That means no more than 2. It's the probability that we have 0 or 1 or 2 alpha particles released. And that is by Poisson e to the minus 3.2 plus e to the minus 3.2 times 3.2 plus e to the minus 3.2. That means 2 particles, 3.2 squared over 2. Yes. And that means that it's about 38%. So there's a 38% chance that there would be, in this 1 second, 2 or fewer alpha particles released. Here's another example. Every day, 1 million people decide whether or not to visit a particular website. And let's assume that each person logs independently of the other. Yes? Now, let's estimate the probability of at least 3 visits. So there are 1 million people, you see. So in this case, we know that it's a binomial distribution, right? We have 1 million trials, and each is a success with very small probability. This is the probability, 2 times 10 to the minus 6. So 2 out of 1 million chance that this particular one person will visit. So each person is like a trial. right? So on average, how many successes will we have? Well, it will be what? It will be 2 times 10 to the minus 6 multiplied by 10 to the 6, and that's 2. And you can see that the average is so much smaller than the number of trials. There are a million trials, and there are only 2 successes on average. All right, so Poisson is a perfect way to approximate it. So the exact probability would have been this. It would be with p this number, it would be 1 minus 10 to the 6 choose 0 times 1 minus p to the 10 choose 6, you know, this expression, yes? But it's, look at it, taking a number to the power of 10 to the 6 is enormously complicated. You agree? It's huge power. We don't want to do that. Here it is, you see, we don't want, it requires multiplying by large numbers. But instead of doing it using binomial, we can proceed because we already saw above that there was a perfectly good approximation, right? What do? We approximate by Poisson, where the average lambda times p is 2. So it's x less than or equal to 3 is equal to 1 minus probability of 0 minus probability of 1 minus probability of is it? I think I meant x bigger than or equal to 3 or something like that. Whatever, right? So you get the idea, right? So each of them is what? So probability that x equals to 0 is e to the minus lambda, and it's e to the minus 2 in this case. The probability of getting 1 is 2 to the power of 1 times e to the minus 2. The probability of getting 2 visits is e to the minus 2 times 2 squared over 2. Yes? You see where Poisson is useful, guys? So Poisson, when it's right, I think of it here as a good approximation to the binomial under which conditions? The conditions that we have many trials. I mean, you have to, of course, estimate what is many. When is it a good approximation? But that's a different story. Just whenever you have many trials and each trial is very unlikely to be successful, so that the average is much smaller than the number of trials, then the Poisson distribution will be a good approximation. Okay, it's also very nice when you don't know the probability of success and you don't know how many trials, but you know that the probability is very small and successes are many. Right? Or you have to know just the product of probability and the number of trials. Okay. And again, a binomial is not required. I mean, even if they are dependent, it ends up happening that Poisson it can be a very good approximation still. Okay. And we're going to try to see it in the next example. So well, you might have to figure NP, right? There is some information that has to be given for you to realize what is n multiplied by p, right? So, for instance, here is the next example. Maybe it helps. So imagine that there are k distinguishable balls and n distinguishable boxes. The balls are randomly placed in the boxes with all n to the power of k possibilities equally likely. So I do not know how. I'm an old guy. I mean, I don't know how to program too well, right? So this apparently is related to some computer algorithms. So this type of problem, I'm not sure how it's phrased there. But here is the thing that we want to find. Okay, so we have n distinguishable boxes and k distinguishable balls. We want to find the expected number of empty boxes. Yes, how many empty boxes do we have after we randomly assign those balls? So what's the solution? Well, we can just represent x as the sum of x1 through xn, where each xj will give you 1 if it's an empty box. So you just then add over the empty boxes, right? So what's the expected value? The expected value of x is n times expected value of x1. They are the same, right? So each of them has the same expected value because each of them is by symmetry equally likely to be empty, right? It's an indicator on a variable, so it's 1 times probability of being empty. So each of the boxes obviously has equal likelihood of being empty. That's how I know this to be the case. Now, what's the expected value of x1? It means x1 is empty, which means all the balls chose to go to another box. So none of them went to box number 1. So they chose out of n-1 options. So first ball, n-1 divided by n, it's the probability doesn't go to box 1. Second ball, n-1 divided by n, the probability doesn't go to 1. So it's n-1 over n to the k. Yes, which is the same as 1 minus 1 over n to the k. And being multiplied by n, yes? Now B, find the probability that at least one box is empty. At least one box is empty. So we can say, well, let's suppose EJ be the event that J of box is empty. The desired probability is E1 union E2. It's one of them is empty, right? Which then I use the inclusion exclusion formula. I don't have a nice answer for it. I just have this ugly answer, right? The inclusion exclusion, here's this formula if you remember it. Yes, it's basically a summation of probabilities of every single one of those events minus every combination of pairs, E1, E2, you know, right? So, and then plus all triples and so on and so forth. That's what this is saying. So it's this summation minus 1 to the r plus 1. And because of symmetry, if I combine r of them together, it's n choose r times the probability the combined ones are E1 all the way to ER. Now, that means that we have all those boxes are empty, 1 through r are empty. That means that every ball went to any one of n minus r boxes. So it's n minus r divided by n to the power of k. This is the probability here. And then when you sum it up, you will get the probability that at least one box is empty. Yes, that's very difficult calculation. Yes, let's say we're now going to try to find an approximation that at least one box is empty. Instead of doing this ugly summation, we're going to try to approximate. So let's suppose, to make concrete numbers, let's suppose we have 1,000 boxes and 5,806 balls. So what do we do? You agree that because we have many boxes and many balls, that let's say that with the expected value is going to be, it doesn't matter, independent or not, it's the same, right? The expected number of empty boxes, we know that. We know the expected number of empty boxes calculated from before. It's 1,000 times 1 minus 1,000 to this power. And I can approximate. What is this expected value? Look at it. It looks, this 1 minus 1 over 1,000 looks like e to the minus 1. Do you agree? I don't like this number. So what do? I place the number I like on the top, and I have to divide by that number. There's a point here or something, right? So it's this. You see? There's a point, 5 point. It's not visible, I guess, but it should be 5 points. In other words, I divide by 1,000 and put it here. Yes, so this is what we get. What is that? This is e to the minus 5.806 approximately times 1,000. And when you calculate it, it's approximately 3. So approximately 3 boxes are going to be empty. So the probability that more than one is empty, one or more is empty, it's 1 minus the probability that 0 are empty, which is 1 minus approximately 1 minus the Poisson, e to the minus 3, which is about 95% that this one is empty. You see, so that's the way an approximation can, because I can calculate the expected value, and it's a difficult question. When exactly can you apply Poisson, and how good is the approximation? But roughly, whenever two outcomes, in other words, when one box is empty, you have 1,000 boxes. When one box is empty, it's not strongly affecting the next box being empty. right? So whenever two of them kind of like this, then when this very weak dependence, then the Poisson ends up being a pretty good approximation. And here is again the birthday problem. So remember that if n people are in a room, then we want to know what's the minimal number of people, n, so that the probability that at least two of them have a birthday is about 50%, right, or more. So how can we solve this question? Okay, so we can say if n people are present, there are n choose 2 birthday comparisons. So there are n choose 2 trials. The trials are not independent, but I can kind of pretend that they are, right? So given 2 people, the probability that they match on a birthday is 1 out of 365. You see, because take 2 people, they can have any of 365 squared days, 2 days of birthday, and they can match on any 365 days. So that's the probability, right? Now, what's the number of, what's the expected value, expected number of successes? It's n choose 2 multiplied by the probability of success. So that I can set as my lambda. It's n times n minus 1 over 2 times 365. Right? That's on average how many successes I will see. Right. So then the probability that the Poisson is bigger than 1. In other words, I found at least 1 birthday, and for this probability to be bigger than 1/2, well, it means that 1 minus probability that y is equal to 0 is bigger than 1/2, and that is the same as probability that y equals 0 is smaller than 1/2, right? And that is the expected value, right? So you see, well, then I take logarithms of both sides and I simplify, and I get this expression. I get ln of 2. And then when I can solve, this is just now a quadratic equation for n squared, right? N squared minus n, just rearrange it. It's a quadratic equation where n is this solution. It has to be an integer, so it has to be this number or bigger. And then when you calculate what this thing is, you end up with 23. Which is correct. You can do the table. You can program a computer, and you can see that you need to have 23 people or more for the probability to be 50%. Interesting, right? You see what happens here. So Poisson allows you to make approximations, and very, very often very good approximations. Right, and very useful when you don't know either the probability or the number of trials. All right, guys, that will be the next thing. I will not torture you today, I guess. You already turned off your screens, which means you possibly are listening to something different, right? Maybe to music or who knows to what. So then I wish you a very good weekend. Good luck with everything. Take care.
Thanks, Professor. Have a good evening.
Mm-hmm.